So hi everyone, welcome to Raaonline. This is Dr. Srivasan, your faculty for biochemistry, and in today's session we will be seeing about the various kinds of repair mechanisms involving DNA. So do you have any idea what's the basal rate of DNA polymerase to make a mistake? Because the DNA polymerase is the one which is going to form your synthesis of new strand. Okay, so what is the rate of the mistake in case of DNA polymerase? It will be in the range of 1 in 10 power 3 or 1 in 1000. So the chance of the DNA polymerase to make a mistake is 1 in 1000. Okay, so is that an acceptable rate of mistake? It is quite good, quite efficient, but you involve 3 billion genomes, 3 billion nucleotides. So 3 billion nucleotides means what? This thing will be unacceptable. You simply can't sustain with such a kind of an error rate. So what we have to do in order to increase the error rate? I mean in order to increase the proofreading efficiency, you need to have various kinds of mechanisms by which the DNA polymerase can do some functions, and through that functions it can actually decrease the error rate. Okay, so we will see all those things, and we also see various kinds of repair mechanisms involved in DNA. Okay, so I told you before, what is the error rate of DNA polymerase? That is 1 in 1000 or 10 power 3. Okay, now there is this function of proofreading of DNA polymerase. What do you mean by proofreading of DNA polymerase? What is the role of DNA polymerase? First, DNA polymerase helps in synthesis of a new strand from the leading as well as the lagging strand of the original parent DNA. Okay, now once it synthesizes a new strand, it is going on attaching the various kinds of deoxyribonucleotides for the synthesis of new strand. The new strand is getting elongated. Just imagine this is your new strand which is being formed, okay, and this is your parent strand. Okay, now this new strand is slowly getting elongated in this direction. Now once this DNA polymerase actually slowly passes on this, it tries to proofread 1 or 2 nucleotides did the attachment, so that these kind of nucleotides have formed the right base pairs or not. Okay, so this is called as the proofreading property of the DNA polymerase. So the DNA polymerase is actually moving in the forward direction, okay, and it is constantly recruiting the deoxyribonucleotides. Okay, for example, here you have got G. Okay, so which thing can base pair with the G? Which purine or pyrimidine can base pair with G? C can base pair with G. Say for example, if by mistake it recruits a deoxyribonucleotide A here, that is quite possible. Okay, because in such a long thing, 1 in 1000 usually happens. So this DNA polymerase, instead of recruiting C, it recruits A here and it just moves on. Now with its proofreading property, it sees behind what it has done. Okay, it is like standing in a long queue and just popping out your head to see whether your kids are there in front of you or behind you, standing in the same queue. They haven't gone outside or they haven't got mixed up or missed. So it is same like that. The DNA polymerase slightly pops out and it tries to check whether the work done by DNA polymerase is correct or not. Okay, this is called as proofreading. Okay, now it tries to look back what it has done. Now upon looking back, it sees instead of C, it has brought a A there. So with the proofreading, what it does, it identifies the mistake. The first thing in case of this repair mechanism is identification of the mistake. Okay. Once the DNA polymerase identifies its mistake, it, with the help of its 3' exonuclease activity, will try to remove that deoxyribonucleotide A, adenosine deoxyribonucleotide, okay, deoxyadeno-ribonucleotide. It tries to remove that A, and after removing that, it recruits the original C here, which base pairs with the G. Okay. So, in this way, the proofreading is being efficiently carried out by DNA polymerase. So, by this kind of simultaneous cross checking after the replication, the error rate can be reduced further. Okay. Now, you just see how much is the efficiency has improved in this case. Earlier it was one mistake per 1000 nucleotide formation. Now, with this proofreading activity, the error rate can be decreased from 1 in 10 power 3 to 1 in 10 power 5. 1 in a lakh, 1 in 10 power 5, 1 in 100,000. So, this is a acceptable error rate slightly. So, also in eukaryotes, when compared to that of the prokaryotes, the eukaryotic DNA polymerase complex will have a very low speed. So, what is the advantage of having this low speed? It can just in a very steady manner, it can easily proofread the thing, and it can easily correct the mistakes which it has done. So, that is the advantage of this low speed of the DNA polymerases, or low speed of formation of new DNA. Okay. So, once you go in a low speed, the chance of mistakes are much lower. Okay. So, by this speed also, the error rate can further be decreased to 1 in 10 power 6. That is some kind of a 6 sigma kind of functioning. Okay.